Is everyone? No one. It's fine. It's fine. I just want to know that I don't wait. Okay. How are you guys? How was Christmas? Good. Good break.
Yeah.
Now full back in. Halfway. Okay. Did you do the homeworks? I didn't have time to check it this time, to be honest. Did you try to work on that? And there was one team who thought about using that in their project. Is one of you guys here? You three? Okay, perfect. Cool. Maybe we can talk either after this lesson or separately again, also because if you really want to use it, it probably makes sense to, like, if you have a grid-based system, that you take these floor plans I gave you, this data set, and make it more into a kind of, that the data set will also replicate this kind of data structure, so that it's also modular, but you can use these floor planes I give you probably to transform it in a way that it's also modular, so it probably makes sense to make it more similar to what you want to achieve.
To be relevant to us as well, but we just have a question.
Of course, yeah.
It's probably a question as well as how to turn, maybe after this course of this, how to turn the 2D plans database library into three-dimensional kind of a voxel-based diagram, so that it's not just flat.
So there's so today we're gonna train first time, right? So there's step by step, but if you are really into that, there's even possibilities to train 3D voxel spaces. And I think if there is really interest, I would even do that extra with only the team who wants or whatever, we can look into that, but it's the next, like, it's even more complicated, let me put it that way. But also, of course, you can just use these images to, like, extrude them or place your modules on them, obviously. So yeah, we can of course talk about that. And also the images we're gonna train on, they're size 128 by 128 now. But of course you could also do smaller ones. Smaller is always easy. So but then if you have, like, let's say you have quadratic modules and then you train on it, 1 pixel could be 1 module, right? So you just need a clever way to have your data and translate it in that. And if you show me your, like, what you develop for the main class, at some point we can think about, I can help you to think about how we can maybe translate that. So yeah. But it's like, I think the thing is more, if you understand how to train it, there is code you can just use. So it's doable, I think. It's just, the thing is, what you need to think about training, even if your code is prepared, it takes time, right? Because we don't have the compute power companies have. I don't have it either, although I work for a company, but we are not like a digital company. So things take a while, right? Like you're gonna train a night or something, that takes time. So, and your computer is occupied. Okay, you have a discussion, I see. I'll let you, that's up to you. Okay. So I guess we get started. You guys ready? Yeah. So we create a new notebook as usual. Okay, so now today we're gonna, did you manage to export the data set as images? Did you do that? Did you try to do it? I'm gonna give it to you this time anyways, but just curiosity. So nope. Did you try to do it or could you not? I think he should be in the Teams meeting. Can you ask him? Oh, yeah, no. Vinay, can you hear us? Sorry, I forgot to add you to the meeting.
Sorry?
Can you hear us?
I can hear you. I
Okay.
just can't see the screen.
Oh, perfect.
Is he there?
Yeah, he's there. All right. So what we're gonna do now, as So you didn't manage to export the data set from the images, or you didn't have time, you didn't try? Yeah.
can see the screen.
Oh, yeah, I don't show it. So you tried but didn't work?
Wait, are we talking about the assignments or?
Yeah. The images? That worked.
Yeah.
Okay, cool. Perfect. So today we're gonna use that. So let's get started. So as usual, we first import. We did that before Torch, which is this library for machine learning, right? And then we will check. So what this does, we did this before. It's just checking if we have a GPU, and only we don't, because I didn't change it to GPU. Yeah, you know what a GPU is. Yeah, so you have to go, sorry, that's German, but it's runtime probably in English, and then change runtime. And then we use a GPU. So I have this because I have Colab Pro, but you probably,
We only have two.
yeah, so we go with that. And here we will see with NVIDIA SMI, we also did it in the past. We can just check what GPU we have. I think we did it in the past, I'm not completely sure, but it just tells the Tesla T4 is my GPU, for example. Now that's the one Google assigns us. So that's a cool little command. And now for what we do today, we have to install quite some libraries. So we do pip install, which will install something. And diffusers is the main library for this machine learning training. And we also specify we only want the training part. And we will run it. This will take some time. Also today, it's not a little, it's a little more code. So I will copy a lot to you, and we won't write out anything. It doesn't make sense. So, and the other thing is we're gonna use, because it's very easy to track how our training is going, we're gonna use Hugging Face. Do you know what Hugging Face is? No. So Hugging Face is something, it's a little bit similar like GitHub. So it's for sharing codes, or in this case, sharing machine learning models. But yeah, it's like an online platform. You can upload models, download models from other people. So like Stable Diffusion, for example, is managed via this company. So we need to, or you need to make an account there. We're gonna do this together now. Go to Hugging Face website. And then we need to sign up. So I'm signed up already, so just probably do that yourself. Just email address, add a password, and log in. And yeah. Did you sign up on it? Did you sign up? I cannot follow that because I have an account already. So okay, give me 1 second. I need to reset my password. I'm sorry. Okay, so, and here we go on our profile, and then we go to settings. So this is your profile, whatever name you gave yourself. Then you go to settings. And then there's on the right side this access tokens, this one. And then we need to copy. So that's, I can show you very shortly. It's like a long number. We need the right token. So go to right and copy it.
The add XFH key or add GPG key. Do I need to add them first?
Eventually, oh, maybe I'm not possible. So if you go here to access tokens, there's nothing. So you go to your profile on the top.
So this is please confirm it.
Just on the left, profile account, the access token, and we need the right token, just the bottom one.
So asking for what's this token for?
Okay, sure. I did this actually in the one and another.
Asking for what's the token for?
And we need a right token before part of
So I just need one, do I?
you can just do both. Maybe in the future you need both, you also the right one.
And then we're using the right one.
Yeah. Okay, so copy it. Then we go in here, back here, and we're gonna write notebook login. And then this will come up, and here we need this token. So we're gonna just paste the token and go login. And then it should say it's valid and the permission for it. It's given. Right.
Good question.
Yes.
What are we setting up for currently?
So this is Hugging Faces, as said, it's like a platform where people upload and share models. And also, if you train models, you can pull. Yes, so there's several platforms for that, but Hugging Face is a very easy one to share things and also to see how your model is training. So it gives you like information about how well it converges, like how well it improves. So it's a very handy website. And also you can, like, for example, if you would work in a team, you upload something there and then someone else from your team can just pull it down without like actually sharing it. So it's a very handy platform, but we could do it without. But it's useful and also especially for us because we just want to see the analysis how our training work without extra work. So that's for that it's very easy. The login you need. Login. And then there should be a window show up and then you need to paste the right token. Yeah. And this one I can just send it to you guys. That's just we need to install some more packages. It's part of that, so I just send it to you. again on Slack. And probably today we're going to do this a few times because it's not super important each of that, right? So now we do something we did in the past. We link to our Colab or drive, right? And then this will ask you also to log in. So now we are connected because we need our data. And now that's exactly what is happening. So we get our data. And now this directory, that's same as in the past. So I have on Drive, I shared a folder with you. So we have this folder on Drive. I can send it again where I shared in the past also the data set with you. If you just open that one, you will find the images. So and then you need to link this again to the folder. So wait, I look for the Drive folder for you guys. And send you a link. So this is the Drive folder, and we need to link again. It's this, as always. So we did this in the past. Also, we need to content Drive, and then you need to copy best like as last time. I sent you this link on Slack, right? Just copy that again in your own folder, and then you need to find that that library. So this is the folder, right? Should look like that. And we need the image data set and these two, the one we're going to use today. So copy the content somewhere to your own folder. Can you open the link on Slack? So, and then that's as usual. So you need to do, last time we had some trouble with it, but you need to find that in your drive. So you go to my drive, and then wherever you put it, you need to reference that folder again, right? So in my case, it looks like this. So this is everyone, we all have the same until my drive, and then after you have wherever you have, and then you just search for the images. So one of the folder contains 10,000 images, we need that folder. That's the data set. You can also use your own, by the way. If you extracted your own last time successfully, you can use that. And in the future, if you want to train on other images, you need to use that folder. Like you need to find that folder to use it to put images. So yeah. So it's until my drive is the same, right? And then you need to find it into your own wherever you put the images. Could you copy the images? Did that work? So you need to take these ones, image dataset, this folder. And then there's inside another one, but you need to reference these images you need to find basically. Oh, there's a problem. Shit. No, actually. Yeah, I think that will take a while. So I don't know, maybe we just download them first and then upload them and we just keep coding and we look at it later again. I think that's the way of doing it. So this one we all gonna have the same, so just the directory where we're gonna upload it to. You know what, maybe I can also send them to you otherwise differently, but you need them on the drive anyway. Okay. Yeah, we look in this later again. So just download it and then upload it, and then we try to fix that later. So you can run it already, but it's not too long. And then the same thing, we need to import this Python script. So just do and then there's this other directory. So there's also this directory called this one. And you need to download this one. And also upload it and reference it. So that's in this one, the content of this one also downloaded. Did you do it?
Yeah, that one's done. The other one.
Okay, and then you can, this one, same thing as before. So you need to, in my case, I just copy it. So in this case, wherever you put it on your drive, you need to, so it's again content. Until here, it's all the same. Content, drive, my drive. And then this is your folder, and you need, but in this case, which is different, we need the whole thing. So at the end, the name of the Python script, Python conditional dgpm.py, we need that. Okay. So this is the same for everyone, and then find it in your folder. And then we also have to add this in this case. So there needs to be a space and then content. So, sorry. So this to your drive where you put it in the end content, and then we reference it like a pipeline conditional, blah, 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 blah. This is the name of the script. We open it, okay. And then we're gonna see if it's working if we run one. Yeah. So there's a little warning that we can ignore that for now. So yeah, if you reference it correctly, it should run.
Then I need to mark the name of the script.
Yes, so it's a Python script, right? So we reference it like any other library. We can do import or from import. So first here we use it, we upload it to our own folder actually. Look, this file at this line, we have it. If you open the folder here, you uploaded it. So now we have it here. Here's our Python script in my
This is destination from.
So you just need the correct address basically. So content, my drive, and then
We need to write the slash content.
yeah, you do that.
Yeah, that's why I would roll that so much to say.
And you need those first. Does it work for you? You need a space before content. What's the slash? No, before the slash. Yeah.
I'm still like compressing it down.
There is, but you can also just download the help with this concept is the express name. Just download, yeah, and then put it to your own folder. You can put it in
Should I put it in the same reloaded?
It's not important as long as you have any like people probably equipped it. It's a total jovial connection. I'll just replace it. Yes, that's actually. And you need to, this one is, this was fine. This one is really, and then you probably, this is not, probably not the correct, although it's in the, like, you need to check your folder again. Like, and for you, can you also go to the finger? You need to do get the other one as this one. And then this is the this one.
Yeah, I also.
And you upload but you can also can you help those people? Does it work for you? Did you?
No, I'm moving.
Okay. No worries. Okay. So, we need to define a path now. I sent this to you probably also. So this command just creates a path here. You will see when I run it. It just will make a new path.
What does RM mean?
I'm not sure, to be honest, but this is a command to create this directory. So that's, so look, like we navigate into a directory here, and then we're gonna create something in that directory. So that's why we need to do it. I'm not sure what it stands for. I just know what it does. And now we create that directory. So this just checks if this directory does not exist, we're gonna create one. By the way, stuff like this is like, maybe you don't even know, just if you would keep using Python and you ever encounter that, just Google it, so you don't need to know all of these things. So now we create it. So we have a new directory here, train data set. I can copy this also. Guys, today we're gonna copy a lot. I just need to keep me reminding me of it also. These are quicker when you copy more. And then we need to navigate up again from this directory, because we're gonna run the script from the other one. So we just type this. We are back in content in the main directory. And the ls shows up as what's in there. But that's not super important what that actually does. Just go over it.
Yeah. So you have two dots. After the center.
Yes, this is two dots, so a space and two dots. This is the same commands. If you ever used, what a CMD is, command line interface. So these black boxes, you know that for sure, right? Window. So here you can also, if you type dir, it shows you. So this is a folder, right? This is my user folder on my computer. If you type directory like dir, will show you anything which is in there. If you type cd and the name of the folder, you can enter it. So I don't know, cd pictures. So that's also sometimes important. And then this is where these commands come from. And cd is like navigate up again. Just just to give you some context. Okay. And now we're gonna load the data set from the images, which you probably still don't have. I don't know. So this is just some libraries to import files, and tqdm is always to show a progress bar. You'll see that in a second. And now we copy the files, we download it, and you need to upload again. It's not there yet, probably. Let's So this is the folder we copy from, and then we just iterate over each file and copy it to our notebook, because we need it online in our notebook. Otherwise, our training will be too slow. If we could, in theory, we could like bring it directly in from the drive folder, but that would be too slow. So we would create a bottleneck. We don't want that. So and now we just copy that. So the name of the file, combine the path with the source folder path, and copy it into destination code. And now we would need that folder, of course. A little bit unfortunate. Maybe I Google if you can reference directly from mine, but I doubt it. No, it doesn't have. Yeah, okay, it's maybe too complicated. Okay, I don't know, maybe we just keep coding and you don't run it yet, because that won't work, but I can show you already, and then we need to run it later when all the stuff is uploaded. By the way, did it work for you with the Python script? Did you help? Does it work for you? Yeah, okay. Okay, so we just keep writing along, and we fix it later. So now this is this function we used, right? So we need to copy it to our folder, so we're gonna use it now. This is the definition, although but now we use it, and this is the directories I defined above. So it will just copy all files from my drive to this notebook. So when I run it, it will show me a progress bar, and then copy that. Oh, it doesn't show me a progress bar. What is it? For you, it cannot work yet because you didn't upload the. That's the thing. So yeah. That's basically our training data, so we will need that, but for you at the moment, it doesn't work yet. For me, it's still running. So this is the upload is also always slow. The internet here is really slow. So we just keep writing, come back to it. So it's gonna be anyway, because the training, as said, also takes long, right? So today we're not gonna train. I'm gonna give you everything to train it, and then you need to train it as a homework. That's what's going to happen. Actually, I can make this short. So I just want to check if there are all files in there. It's just to see, because you should know how large the data set is. So we just will check if that's correct. So we can nest a lot of functions here. And for example, for me also, still uploading, so it won't spit out what I wanted to do. But this line will just tell me if we're gonna have 10,475 images, and this will spit out this number just to check if everything's uploaded. But as you can see here, this is my progress bar uploading it, which is also slow. So yeah, that's a little bit of a problem. I'll run it later. We will need it then. Didn't expect that. So this will show us the length of the data set. Now, next thing is we will just, because also one of your homeworks was to find this kind of extra thing about a data set, right? Like the size, the connection of the floor plan. So now I just gonna give you, actually, we're not gonna write it, a very short, in this code, we just also do this because I'm not sure how successful you were with it, or like to just make it quicker. We're also gonna get the size, and we can get the size of the floor plans also from the images. So I give you a small code. Oh, now it's boosting. I give you a small part of code that will just take the image, check for the background, and then tell me how large that image is. So yeah, I copy it to Slack. I'll copy it to Slack. Just paste this. So this will just tell us how many pixels a certain color in this image has. And my upload is finished now. I can run this. It's gonna hopefully tell me, yeah, 10,000 images. So, perfect. So please, if your downloads and uploads are finished, let me know. Then we're gonna come back to that. Upload it. I think, but normally it says it takes longer than it does in the end. But just let it go. Leave it running. And the thing is, you will need it for the homework latest. So if you don't make it today, it sucks. But it's not end of the world. Okay. Did you copy that? Are you here? Are you guys with me? Yeah. Okay. So now we're gonna. I think it's quicker. It's not. Maybe it's still an hour though, but it's not 4 hours. So we just test the function I gave you above. I can also copy that basically. So we are looking for black pixels in an image because the images, yeah, I show you one maybe quickly. Or you have them, right? But they look like this, right? And we now count how many black pixels we have to find out how large the floor plan is, right? It's quite straightforward. So yeah. So this is what we're gonna generate also approximately. Yeah.
So we are throwing all of these data into this thing. So we have this study, and then it can then generate the floor plans again.
Yes, it will generate new floor plans which have similar features.
Yeah,
but it's not the same image. That's what we are going for, actually. Yes.
then we can control it by saying, let's say, how many bedrooms or how many.
That depends. That depends on the conditioning. So today, that's why we look for the size now. So I'm gonna show you how to do the size. That's straightforward. It's the simplest version. But of course you can and that's going to be the final assignment. You need to train it, and if you want and can, condition it differently. So that's what you like. After this, you're gonna have 1.5 months, so even a little more to do the final assignment. I think till end of February. I have to look it up again. I sent you that again, and then you can eventually train on a different condition. But today we're just gonna do on size. So you can tell it size from 0 to 1, which like size you would have from the range of the flop, like all the flop and tests. So the 0 would be the smallest size, 1 the largest size the data set contains. It will generate similarly sized images. That's called conditioning. Okay. It's the same, by the way, the same if you use Stable Diffusion or Midjourney, right? It's the same technology, but just way more successful, way bigger, way longer trained and all. But the condition there is the text. It's the same thing. So we're gonna condition on a number, and the text there is something called tokenizers. They transform text into numbers. So it's also conditioned on numbers. But we're gonna condition just with one single integer number, so it's very dimmed down, but it's the same technology. Yeah.
You know that
We just check if this function is running, but basically you copied it actually, probably we don't have to. So no say this function, we're gonna call it. And test it with the image we opened. I think, you know what, guys, also copy this as such little time. Sorry for that. I think if you have questions on the code or anything, just ask. But I think today is not so much the focus. It's most of it is stuff we did before. Not everything is maybe super clear, but it's not important. So here we would just a unique directory. We just check we just test the function. So just hopefully stick. Yeah, so this one has 5,336 black pixels. One example image. That's just to test my size function. And now, because same thing, like we could in theory find the size of it every time when we run it, but it's easier to save it as a JSON file on our directory. It's gonna make the training quicker. So I also gave you another function, which is a large one, but just copy paste it, which will, so before here, this one, we take an image and look for all the black pixels. Here I tested only, and this, what I just pasted here, I will give you in a second as well. This will run this and then set the range. So if the largest image and the largest size and the smallest size have a certain range, right? And we're gonna rearrange this value of ranges from that size to 0 to 1. This is also happening in here in this part. And then we save it as a JSON in our file here that we can use it as. So we're gonna have an image and a JSON file with the same name. And that's actually, that might be a problem. I don't remember my own code. We will see. And then we're gonna like use them together. So we feed the image to the network, we feed the JSON to the network, and it will train conditioned on these two things. So just use that to generate a JSON. And I will give it to you again. How's the upload download going?
1 hour 54 minutes.
The download or the upload?
I mean, upload.
Upload.
Some image, like a citizen image.
One question, that's because I just saw it on my own. It's called copy in front of the image name, right? Okay, that might be a problem. To be honest, that should not be, but I think I can fix it in code also. That's my own mistake, not yours. So because I copied them and it seems like Drive renamed it. Yeah. Yeah, I'll do. Okay, let's continue. And yeah, now we're gonna create the labels, and that's also something you cannot do when you don't have the images yet, unfortunately. So it's the same as we did before. We just check if the label is there. And OS. So what we're doing here is just we use that we create these JSONs, right? So this is the save plan size from file. This is the function I gave you. We just generate this JSON. And then we are already moving into the training of that. So problem is that so I run it now, you can see it here is executing, and you cannot run it because the images are missing. So yeah. So this, for example, is just an example. This is a little example now. So there's like 0.3 something instead of the actual pixel size because we need the range 0 to 1. That's what we just did. And now I'm not sure what we do because you should run that. Okay. So the next part will be, we did this before once very shortly, I think. It's called a data loader, and I also give the whole one to you, because otherwise you're going to spend ages here. But I explain to you what it is. So first, we need to import a lot of packages. Torch again is our main machine learning package. I send it to you. You don't have to type it. So this is what we import. And then I just show it to you before I send it to you. But basically, this is a so-called data loader. Okay. So it's a class, right? And it inherits, that means it inherits from a data set. A data set is, here we import that, so it's a part of Torch. So this is something these machine learning models need to pre-process data and then feed it in the network. And it will open the image, and then we can apply transforms on it. That's actually the only important thing here. So this one, we create this data set, and then we open an image, we open the directory, we open the label. So we open our number for the size and we open the image at the same time, and then we can add transforms, which is for images quite important, because transforms, what is this? It's mirroring, rotating, flipping. So, and why do we do this? So we can tell it, if it opens one of the images, it can additionally rotate it 90 degrees or flip the image, mirror it, because then we have 4 times, if we rotate the image 4 times, right, our data set is 4 times larger. So our network is able to learn more. For a photo, we couldn't do flipping, and we couldn't do rotating, because then it would, it doesn't make sense to feed the network differently orientated photos of a dog or something, right? But for floor plans, it doesn't matter, because the orientation can vary heavily. So we can artificially make our data set way larger. That's why we use transforms. So that's a rather important part here. Yeah. And that's everything else to get a item says. So it will parallel open the image, open our JSON file, and then load to feed this into the network. And yeah, that's basically mostly what this is doing. It's just a preparation for the data we loaded into our notebook to feed it better into the network. So I send it to you, and we just paste it. But for me, it's more important that you understand this transformation can be very useful, and when to use it, when not. So yeah, because floor plan is perfect. We can rotate it 90 degrees in all directions. We can, at least ours, it's called Manhattan grid. I don't know if you have, it's rectangular, right? So we can rotate it 90 degrees in all directions, and we can flip in both axes, and it's still solid floor plans. So yeah. How is the upload going? I'm gonna keep asking this one. Shit. And as last time, also, by the way, I'm gonna send you all of that, also with comments. So for example, if you wonder what was the data set, it's gonna say that. So yeah. And now, because I just mentioned it, we just quickly write it. Maybe so transform is something we did this in the past, once very shortly. So we import it, and we create a transform that we can use it on our data set. So we will also, for example, need our rotation data set. And that transform is also a class. Oops. That's, by the way, that's the name I gave it. It's not a very elegant one. Please don't now copy it, but if you write code yourself, don't do that. And this is what we are doing here. Basically, we have to write this because this 90-degree rotation I mentioned is not existing in the libraries we are using. So we just need to create that transform because it's a very special case for our floor plan stuff. That's the rotation. So we initialize it. We just need it, and we can use it the same way as other transformations. So yeah, we need to create our 90 degrees, so we can give us like several different ints, and then we're gonna choose a random one. So we're gonna give it 0, 90, 180, 270. So all the 90 degrees rotations. And then we can add our transforms together. So this is just, yeah, probably, by the way, I import packages a lot. Doesn't really matter. It's not elegant, but it's. So compose, I think we did it in the past. I'm not completely certain, but it just adds together different transformations. So V2, by the way, there's a version 1 and version 2. For some, we need V2. So we want to do horizontal flip randomly. So V2 random horizontal. By the way, you also have autocomplete probably, right? So you can also, do you have this? I think so, right? So you can sometimes use that as well. So like this, so I want this, it tells me that already. You can just click it, or you can tap. This one tap, then it's auto for it. And then now we also, so we either randomly flip it horizontally or vertically, and then we're gonna use our own, so the my rotate transform we just wrote. And here we can define this rotation angle. So either 0 degree or 90 or 180 or 270. And then we normalize. That's something I told you earlier. We did this for this range of our I just type it out first. So we did this with the range for the sizes, right? So we transformed them from the smallest to the largest to 0, from 0 to 1. And now we're going to do the same with the image, which is a little bit, that makes the network train it better. That's why we do this. So at the moment, the pixels are from 0 to 255, and this one will make them from -1 to 1. That's why and then the networks perform better. That's just what people found out about it. So how's the upload going? Maybe we're there at the end of the lesson.
So what happens if the rotation angle is, let's say, 0, 30, 60, 90, 120? So it's not just always vertically.
Can happen, like you can do that, but actually, if you have time, you can try it. But it's probably, so you could have also random transforms in between that. You could even, that's like, then you don't need there is also a random transform. Look, if I would do V2, I think at least, maybe I have to Google it, but random rotate, something like this, does it exist? No. But there is rotate. So you can make that. I wrote this only because then you couldn't specify numbers. So you can put rotate, and it probably will just randomly rotate. But the thing is, so if we had, how do I draw this? Open paint. And so our floor plans are all Manhattan grids, right? So like this, something like this, whatever. So if we now rotate some of them and we have something like this, right? It's really bad written, but you know what I mean. Like I just rotated, but also on Manhattan grid. That probably it only knows either these kind of rotation or this kind of rotation, but it never knows the mix because we don't have floor plans which have like angles like this. Our data set doesn't have that. So it will learn these ones separate from these and eventually do very weird overlaps of it, but it won't learn, like, for example, this is like would be a very specific corner, right? So it convolutes, you remember the convolution, so it would convolute over one of these corners and would learn it as how these like different angles come together. But if we only have this and then this, it never sees this kind of angle, so it's unable to learn it. So if you had a data set which had non-Manhattan grids also, you could also experiment with the rotation. But since we don't have that, it will never see angles which are not 90-degree multiplication, so it won't work. Probably. I didn't test it, but
So then if we want to train our model to do something that, let's say, to do an architecture that jumps out of the grid, then we need to have the floor plan that is kind of.
You need a data set which knows so basically what you can think about what these networks are learning. These networks are learning features. So that's why like this, for example, would be a certain feature. So this kind of corner is a certain feature of this image. So it learns features and then learns how they sit together on different sides. Like it either learns the whole agglomeration and then always smaller into the features. And then it is able to recreate them and like reposition the features differently, somehow like abstractly spoken. So if you want to have a data set which, like if you want to have a network which can recreate features, you also need a data set which has these features. So it cannot create something it has never seen, although of course, if we have really large data sets, like think about Midjourney, right? That creates images we have never seen, but it's all like combination of a lot of small features. It combines differently, and in our case it's a rather small data set, so this is quite important, and the larger it gets, the more abstract become these features, right? But in our case, yeah, if you want to have like a network which creates non-Manhattan shapes, you need a data set which also has that. Yeah. But by the way, what you could experiment with, but so because the data set I gave you, it's not images, right? That's a pain because we had to make the images. So, but on the other side, what you then can do, you can, for example, you could like take a grid like this and like transform this. So you could take in Python this like this floor plan and then like transform it, like same as in Rhino or something. You could do that, although of course everything is tilted and shifted and weird, but then you could create from that again images, and then you could transform that data set also. But that's probably too far off for us, but just in theory, also a way to work with that. Yeah. Back from my beautiful paint drawing. Okay, and now we create our data set. So our data set means in that case, I've sent you earlier, I sent you this class, this very large, this one, custom floor plan labeled data set. So this is also, yeah, this will just call what I said earlier, that will call different items from our data set and feed it into the network. And here we define it. You remember classes, you first define them and then you create one. So now we need to create a class of this data set, although it's not the actual data, right? It's just a data loader kind of. So this is just, yeah, we create that and feed in our transforms and the direction of the directory of the labels, which you probably don't have because you couldn't create it yet. Hit run though, sorry, 1 second, I'll be right back. And it's complaining. Ah, it's like this. Okay, so now it's gonna get, I copy paste it again, you don't need to write that, and we try to talk about it. It's also a little bit commented. So this is a config file for our training. So image size needs to fit the images we feed it, of course, right? So it's in our case 128 by 128, so that's fine. Then train batch size, that is dependent. That's, we give it more than one image. So if we like, you have to imagine like this always, if you train the network, it will feed from the GPU, from the CPU, so from your computer to the GPU, and it always can give it more than one image at the same time. So this, if your GPU is stronger, this can be higher. If it's weaker, it has to be lower. So in our case, 16 is fine, that these settings work. I just go over it a little bit and tell you what they are meaning, because then you can eventually change it. Similar to this one. So this is how like evaluate. So we always do training and evaluation. So you train, and while you train, you also output images and check how well the network is performing. And you can also see like in between images. So it shows you images, how it's progressing already so far. So that's the batch size, same thing as for the training, we keep it same. Epochs is how long it trains. This is important. This is what you can really change. These are, by the way, it's called hyperparameters. So this is the ones you can, even if you have the same network, you can tweak these to improve the performance of your network. So the number of epochs is basically how long it will train. It will train the batch size and multiplied by the epochs, right? Because one epoch was like, it feeds one batch. So this is something you can tweak and change. And if you do it shorter, it's quicker, but performs less well. If it's longer, there's a point where it converges, it doesn't improve anymore. But if it's longer, in generally quite a while, it will improve. In the beginning, it will improve very quick, and then it will improve very slow, but still improve. And the learning rate is how strongly you want the network adapt to your data. So this is something you can also play around with, but this is a good size. So for the beginning, honestly, I wouldn't change those. It's just in the future, you know what you can change. This one, you can only change if you have more than one GPU, so basically you can ignore it. And this one is, yeah, this is the easiest one, just train longer. Most of the time, if your network generally works, training longer will improve it. That's like, roughly, you can say that. And the learning rate, if you do it smaller, it will probably have better outputs, but you have to train longer to have meaningful results.
Is there any relationship between the training match and the evaluation match? Like, do they have to be the same one?
No, they don't. But it's just, so you have to imagine it like this. You feed the network not one image at the same time, but you can feed it, in this case, 16. So you get 16 image. It can be different, but it doesn't make sense to make it different. It's just, it's more about, you want this as, so if your GPU can handle more than 16, it's even good to set it higher, because then the training will be quicker. So, but most of the GPUs we use, or also the Colab 16 is kind of the max of these images. Maybe you could try, and it's also good to be in 8, like in hexadecimal steps, so 8, 16, 32, stuff like that, right? But it's not a must also. So I would just leave it with 16 for now. Yeah. This one I wouldn't change, to be honest. And this one is, when the learning rate, so the learning rate is adaptive, so you can do this when it will start to change. But it just this one I wouldn't touch. Maybe this one, maybe, but and this one is more for the output. Then it's basically, so this is the settings for the network, and this is more than we save it and stuff. So we save images always to test to see how the training is progressing, and also we save the model every 10 epochs that we have. Like if it fails, for example, we have a in-between checkpoint, right? And mixed precision, yeah, this one it even says that here. So this is that will increase the size of the network. That's also a different like level how the bytes, how the actual model is saved. But 32 is better, but 16 is fine for our needs, and also just leave it. Yeah, this is the name. So this one, so mine is called DDPM floor plans tutorial, but you can call it my money network, whatever. That's the name of the network. So it's completely changeable. And push to hub means if you want to use it with the Hugging Face, hub is Hugging Face, so we just keep it. Private repo, I have it on private because I don't want anyone, if it's public, anyone can download it, so I have it on private, but you can also do public, it's nothing to lose actually. And yeah, override output here is if you retrain it on the same name, if it will override it. That's it. And seed, yeah, seed is the seed it starts to generate, but that's also, you can ignore. -1 is random, but 0 is fine, then you can, it's reproducible. Yeah, so this is what this does. And this is if you train your main, the main thing you can change next to the data set. Of course, the data set is important, and these settings are the main things you can tweak to make it improve, to make it train quicker, make it train better, make it whatever. So yeah. So again, this is the code. How is the data upload?
90 minutes left.
90 or 19?
90.
Oh, okay. I honestly, I didn't expect that. I thought it's gonna take a little bit, but not several hours. So now we test our data loader quickly. Oh, I probably have a, yeah, I have a spelling mistake. I didn't run it. Okay. So this one.
What does IT have some calculator?
Okay, this one, I think the name is one because so this should be. I need to import. Okay. Where is it? This one you have fed. Did you change that? So two things you have to change. One is import pill here. I forgot that. And the other one is named this one train data loader. I think I call it train data or something. Okay, and what we have to do is no, train data was correct. Oh, I'm sorry. Please go back up and call it train data. I forgot I skipped a line. Okay. Because now we define train data. Sorry, so train data. Did everyone catch that? And now we create data loader. Data loader. I didn't know it. So if this, I hope you may have some typing mistakes later because you cannot test it right now, right? Because the images are missing. So maybe I just give you my code then later. Let's see. And now I just load this, just loading one image from the data set to just quickly test it if we can look at it. Oh yeah, it's a church.
Hello.
So we just visualize it. I will give this code to you. So it's just, we did this in the past. It's just quickly to load one and change it and transform and see if we can see one. And will show me one of, this is one image from the data set, right? So I give this to you again. It's a recording anyway. And now I also give that to you. This just shows 3 images, and then we have like, this is our size tensor. So I rounded it also. So each of the tensors has only one number. So we only have 10 different numbers now. We have only 0 to 9. We don't have everything in between. That would be possible, but our data set is probably too small for that. So it's better to just, but that's something you can experiment with if you ever want to train on different labels.
And does this always round up, or it depends? For the lower tests, so it's always round up. Let's say 3.1, but they round to 3.
I wrote that, so it doesn't have to. But I think in the data loader, I just experimented with it myself and I found out it performs better if I round it. But you could also do it between 0 and 1. It's just, it's a little bit, if you would imagine it's like a 2D plot space kind of, and you, by giving it a label, we have multiple dimensions, right? But if it would be 2D and you give it a label, it would push all the data to certain points, directions. So then it will create something from closer in that bubble kind of. So if you have like larger numbers, it will shift it more, so it makes the distinction more clear. But that's also, to be honest, this is kind of the edge of my own knowledge. So I don't really know how that performs. I think there's, oh no, I can unmute mine. I think mine is full.
Thank you.
Another question, yeah. So for the floor plans in here, are they all it's one single floor? So is there anything like, let's say if there's a building that has the floor and has 2 floors, and then the 2 floor plans are somehow internally connected?
Well, so this it's only single ones. But for example, do you see this one?
Yeah.
This has the green stuff is a stair.
Oh, right.
But the information we have is only 2D. So it's not, you cannot make 3D from it. The thing is, that's also why I show you 2D. I thought about doing 3D. Problem is we just don't have a data set, right? So that's the problem with that. So if you could, for example, if you would generate data differently, you could train 3D. But for what we want, so example, if you would say you have like different boxes and they symbolize spaces, right?
Yeah.
We don't have the data, or I don't have it. Then you can generate it with different algorithms, but then it's kind of like a snake biting its own tail, because then you could also generate, right? So it's a little bit, you could generate it directly, but this is a data set someone else agglomerated. There's different ones with floor plans that's existing, but with 3D, difficult.
Yeah.
So that's basically why we are doing 2D here, to be honest.
It's just because these are very cool.
They're pushing the 3D.
Yeah, they're quite in the 3D part, and then they sent us this kind of booklet done by the past students.
Yeah, it's like reinforcement learning stuff, I know. I think the thing is, if you could create data yourself, right? But that's a whole different project, basically.
Yeah. We think it's going to take a very long time as well. Not sure if we can, if we can gather that data, etc. Secondly, yes, probably not going to be as competitive as these ones. And yeah, just
the thing is, if you have data, if you happen to have a data set with maybe 1,000 3D voxels or something, I'm very happy to help you to make that. The thing is, I don't have that data set, so that's.
Do you know if in this case, where can we find 3D data sets?
Yeah, I don't know, otherwise I would have it.
Okay.
But it could exist, I'm not sure, but I don't think so, to be honest, because it's very, like, it's a very specific interest, I'd say. It's not very, like, a floor plan is something a lot of people try to figure out, so it's kind of, it's out there. But the 3D is also because that's actually the potential of it, because you guys are working with these modules, right? And that's like inherently a pixel is like a module, so that's kind of overlapping. But of course, the data, that's a very specific interest, like no one else probably ever did something like combining the modularity with that. So there is no boilerplate 3D data set like that.
So then in this case, if we're going to use these 2D floor plans, then we're basically slicing the architecture into different layers, and then
you could do that, yes.
Okay. Yes. And then then that comes to my next question, because you said the green part was the stairs, so basically the circulation. Then if we are going to regenerate these different plans for our, in this case, architecture, then how do we generate the floor plans that it's different in different levels, but then the green part always stays the same area? Or stay-
But that's actually not a problem, because if you had, you could, but I mean, that's not machine learning then, but if you want to do that, you could just create two which have the green part. Not all of them have it, right? That's maybe also a problem, but you could also filter out the ones which have it or don't have it. And then you could start like slapping, just saying, you don't define the outline then, but you could just say they are on top of each other where the green is, right? But it's a little bit a hacky way around.
Yeah.
But you of course could try that. But yeah, the thing is that what Federico and Cesar showed you is a very, very different, it's also AI, but it's a different way of generating stuff. So
Yeah, and
It's-
we can't see how in terms of what they are saying versus what this is showing. We can't really see the link.
you know how to bring it together, yes.
Yeah.
Yeah, well, the problem is the data set is unfortunately very simple, but because there is quite successful algorithms which do that also with 3D, but I cannot just download the data like the floor plans. So
Yeah, and also with these plans, let's say, will there be any codes kind of merge, let's say the Tesla 7 with the Tesla 3, that these two units become one thing, but they're somehow internally connected? Because let's say we take these as one unit within our project, and it's definitely not going to be a standalone unit. So it's going to be connected with the others. So is there any code? Are we going to do any codes that can put them together into our architecture?
Well, there is networks which are trained to that you give it an input image, and it will generate something based on the input. So that's like called image to image networks. Then you could, but you still would have to find the outline. But what you could do with those is more, you could generate several and then have a separate algorithm trying to combine them. But would not be AI, right? But you still could look into that, because the outputs, it's quite straightforward, because the backgrounds are always black, right? So it's very easy to like separate them, and then you can of course look same as your, like if you take different modules and you say make them stick together, you could use like you could generate first the floor plans and then try to add them up in a different way. Or you could, of course, if you had a larger, like if that image wouldn't be a single floor plan but multiple, you also could directly generate a multiple one. But that's something I don't have the data set either, so limitation of this method is not what it can generate, it's more the data. So that's also why I put so much in the beginning, so much focus on the data set, but now we still have the same problems. So, but yeah.
Okay, thank you.
Should we wait for the others coming back?
Go.
I'll just ask them maybe. How's the download going? We can also just do a short break.
About 12 minutes.
Okay,
10 minutes.
that's fine. Let's just do a 5-minute break.
Then
Oh, hello, Crystal. Hello. Hello.
Yeah, but so just one last sentence for the 3D. You need to either find data or generate data. That's something I unfortunately, like I tried before I prepared that class, I tried to find 3D data and I didn't. So that's, yeah, I don't know. So okay, we just do one last here. So we just show the images. Did I send this to you, by the way? I'm not sure. Do you have this one already? These two? Did I send that to you? Did you write it? This one just shows several images with the. Not super important though. I could just send it as well.
we see the one before as well. Yeah, we have that. Yeah, we don't have the last one.
So just also about data set quickly again, I think there's one team, I think it's not you two, it's you three, right? You probably more gonna, like, for you, it's more important also to have a fitting data set. And for you, if you would want to do it 3D, it's a whole different problem because you would need to have like boxes, like for example, something like there's these algorithms called box packing algorithms where boxes are like stacked on top of each other, and then how they, like, you avoid that they collide and stuff like this. This could be a way to generate data, for example, but then the AI would only regenerate the data you generated differently. But that's like, you could of course make synthetic data like this. So I would highly recommend to try, or like it would be really cool if you could do it, but I understand it's a whole different problem.
So then,
So-
yeah, it's probably just gonna be architecture sliced into layers, and then you use the 2D plans to make the thing. So,
Up to you. That's whatever you come up with. But as said, you can, what you also, for example, what you could do, so remember, but then same problem, data set, but you don't even need to train a different network necessarily, because so you remember that a tensor is like, an image is a tensor with 3 numbers, right? So we have RGB. So you could just say one of them tells you how large, like how high that is. So if you had like each of your pixels is a module, right?
Yeah.
And one of your pixel values is not a color, but it's the height of the ceiling. So you could encode even in this without a different network, you can encode 3D data. But same problem, where's the data set? So because then you also would need a data set. But what you, for example, could do, take something like this floor plan and then say that the different colors have different heights, for example.
Okay.
But if you encode it correctly, you could do that, but the problem is you need the training data set, right? So you would first need to make the training data.
How do you let the graph of the training page where
If you have, for example, if you have a Grasshopper script, which makes you different geometries a lot, very easy. I mean, it's doable with Grasshopper. If you have, like, if someone from you works on that and needs help on that, I also can help with that. But it's a different, like, it's not this, right? You would, and then you can do that. You can like make a Grasshopper script which generates this kind of data, and then have an output, save maybe 2,000 would be good. But if you have a generative script, that's fine, and then you can give it back to the AI. So that's possible. I know even someone in Bartlett did similar stuff before, by the way.
If we are doing like 3D models in the Rhino, and as you said, like doing the script and it can and having outcomes, which is our data set, and
So
it's still as the picture, like when we training the data, when we input the data and training the outcome still is the pictures, right?
yeah, but a picture is just information encoded in a certain box, right? So let me pull out Paint again. Where's the mouse? So if you have, this would be your image, right? And you imagine your image in 3D because you have 3 layers, right? RGB. And then even if it's, and each of the layers has a number from 0 to 1. So each pixel, 0 to 1, right? 0, each pixel, 0 to 1. So if you would say one of those is not a color, but it is, for example, you split just the 0 to 1 in 5 parts, so your building can have maximum 5 floors. It's thinkable, right? So then everything, or in 4 floors, so everything from 0 to 0.25 would be 1 floor. Everything from 0 to 0.5 would be 2 floors. So you just encode information in the same way. And then you could extract it also again, right? So that's absolutely thinkable. And then even you could, it doesn't need to represent colors, right? That's the most important part. I also try to teach you with the tenses and all. So you can, for example, let's say this would be height of the building, and this could be function. So thinkable, right? So, and you could even have, like, in theory, but then you need to change the network I'm showing you. But honestly, I would also try to help. If someone wants to try that, I could help with that. Try to help with that at least. You could have more than 3. You can have 4, 5, possible. So it's more about how can you encode your info, like you have information, you need a data set which stores information, and then you need to think about how to encode it to feed it to the network. Yeah. Okay. And especially the thing is, one other thing, so 2D, if it's only, like I said before, 2D has only 3 layers, like, but it's already 3-dimensional. That's the thing. An image is a 3-dimensional data object. But if you have 5, the same network will still work probably. If you have 10, gonna get less good. If you have 64 something, it's gonna be even worse. So then at some point you need networks which are also, because in this we do our convolutions only 2D, so we only check in this direction our neighbors. But if you have a lot of stacks, you should also check what is above and below, very roughly said. So you need a different network architecture at some point. But if it's like if it's only a few numbers, or even if you encode the height of the building into one of them, like 0 to 1, and then that can tell you 1, 4, 3, 2, 3, 4, like how strongly extruded, that's a perfect valid possibility. Yeah, well, AI is complicated. But I mean, honestly, if you have an idea in that direction, let me know. I help. It's the only I can do. I unfortunately cannot provide a 3D data set. That's the only thing I cannot do. Okay. So I copied this, but did I not? Did I?
Paste it.
Oh, I lost it. Sorry, I need to reopen Slack, I think. Let me close that. So this was that one. This will just show these different pictures with the conditioning, so the size in our case.
Okay.
Okay, and then you don't have another skill module yet, right? So you didn't have one where they train you to generate stuff with Grasshopper, Houdini, I don't know. Okay,
No,
that's probably.
we weren't gonna have that, but so who was gonna teach that is didn't get his visa, so we don't have that course anymore.
Oh, that's a problem.
Yeah, and so yeah, that's a thing that we can't. We'll see how Python is going to be put into either Grasshopper and stuff. But we are going to have a skills module for Unreal.
Unreal, yeah, with Danny, I know.
Yeah, this Saturday. So yeah, that's
The thing is, I mean, I think also the base idea from Cesar and Federico is some degree to integrate that directly into something like Unreal. But if that's not, if that's missing, that spot kind of, you can also just like train the network, use it externally, and then bring the data in. That's way more doable. For example, JSON files you can load into there, but yeah, I think I also, let's see how that develops, but I'm probably gonna be, this is our last like full class. I just let you train, then we check in again, but I'm probably gonna be present and try to help you with these things as well. Okay. And then this one I also, that's a very simple one, maybe just, yeah, I can also copy it. We did it in past, it's just showing a single image. We maybe use it later, or probably use it later. So like this. That will just show one single one. That's just a useful function to have. Okay. Probably should have packed all of that into a different.
7 minutes.
Still, okay. Okay, now we get to the actual AI. So what we did above this one, right, this is like our configurations. And now we define the actual AI model. So I first copy it and show to you. You don't need to write it down. It's just about a little bit of understanding. So this is the core of our diffusion model is a UNet. I just show you one very quickly, an image, but it's I think I showed it to you before. So this is the core of our neural network, and we need to define how that looks. Just roughly think about, we feed in our image here, and then it will compress that into different dimensions, compress it again, and each of these is a neural network. So we have several, we have more than one actually learning parallel. This is one, this is one, this is one, this is one, this is one. And that's how it looks, and we now need to define that in our code how it looks, but we don't need to learn about other people from computer science figured out that this model works very well and they trained it a lot, so we just take theirs and say that works, that runs. That's kind of a representation of it, but it's not what you need to know. That's just explaining this. So for example, this one, if we say how this model looks, down block is this is a down block. So from here to here is a down sampling block. So yeah, that's what we just do. But also me, I copied that from the internet. Like I don't, this is very complicated stuff. And if you need different image sizes, you need to change that eventually. But this is basically telling us in code how our model actually gonna look. And here's, for example, this is our input size, and then we model it down until a different size, and then we bring it up again. This was this says, and skip connections and all. That really goes beyond what we need to learn. But this is our base model. We call it also model is our base thing. So yeah, and this is the down block, up block. That's why I showed you that it makes that at least a little bit understandable. This is the down blocks, this is the up blocks, right? So yeah, that's it. I think more extends really what we need to talk about and know. So I also give that to you. And I think most of the rest of the lesson gonna be more like this. So copy, paste, I explain. I hope that's fine. Oh, and there's one thing missing in this one. And this is our conditioning. So this is an unconditional unit model at the moment, which is also perfectly valid because you can also feed it with images and then it will just generate something randomly similar to the images, but we want to condition it in our case in science, right? So if you want to change the conditioning, that's also important, but you need to, this is this class embed type identity. And then there's another thing. So if you ever get to the problem, just ask me for it again. But if you now this is identity only works, this kind of embedding type only works with a single number. If you have a larger tensor, so for example, if you would want to do the connection of the different rooms, you would need a different embedding type, and then you need best just ask me for it and I will help you with that. So and now we just need to do data set because from now on just recall this in training data, yeah. Maybe it's called train data, I'm not sure. Yeah. Okay. So what we are doing now quickly is we just check one image from our data set to see how it looks. So I also copy pasted. It's all tensor stuff. We did that in the past. So this is from our data set, the first image and the first size vector. And then the second one. And then we just, yeah, I just run it and then show you what it does. So this is the input shape of our model. So basically we know that 128 is the image size. This is the RGB vectors. And this, what is this one doing? So this is you remember the batch size. The batch size is actually an extra dimension. So that's just, this is in our case will be 16 then, and now we just have one to test it because we need to use it like that. And this is if I do unsqueeze, I remove that dimension, then I can visualize it again. But for feeding it into the model, we need this extra batch dimension. And what we also can do now is we can check if our model will create the same thing. So this is our model. We defined it here, right? We called it model. And now we just want to check if this will create the same data. So it will now create completely nonsense data because it's not trained yet. But yeah, we check it's the same shape as this. Yeah, perfect. So good to train. Okay. I think you don't need to write that even. That's just testing.
Yeah,
so
I just wanna.
it's gonna.
Yeah, you can just quickly explain this part again. So the sample image 1, size 1.
So this is here data set is our data loader. So we have this 10,000 images, right?
Yeah.
So here we take index 0, like the 0 number from our data set, and then sample image and data set 1, we take the second one basically.
Yeah.
And then here let me show, like I ask you to show me the shape, right?
Yeah.
And here I do unsqueeze. Unsqueeze will remove a single dimension, so it will remove that dimension. That's all I do here basically. And then here, so do you remember the diffuser image I showed you?
Yeah.
Oh, that also extends maybe what we need to know, to be honest. So I don't know what, okay. So what we are doing here, we give it always a time step. So basically we always have an image and we add noise and we learn in a time step, in a frame from at certain time steps, also always what the time step, which noise to add. So we also need to feed it the time step. But honestly, seriously, this is actually, I didn't really plan to talk about that too much. So that's what we need to do here. We need to do a fake time step, which is the zeroth time step, but we need time steps from 0 to 1000. But it's all in the code I give you. You really don't need to take care of that. So, but I need it to feed it for asking it. So in this case, this is what if the model is trained, I need to also, like if I want to make it generate something, I need to ask it for something specific. So I need to feed in a certain noise and the time step and this label, and then it will generate on that something. So what I do here is only testing if my dimensions match, that my model, the training will be successful, hopefully. It's just to see that this is all running, but this is basically asking the model to generate something. But at the moment, it will generate completely random things because it's not trained. It's just testing that this matches with this one. Because that's the thing. This is what I will feed the model, and this is what the model will spit out. So that should be the same. Yeah. So as said, we're gonna keep copying stuff today. So now there's the thing called noise scheduler. So I also run it. So this is from our dataset images with added noise. And noise scheduler means, so I leave this maybe. So here I add noise, right? And I can add noise in a linear fashion. So you know, like a linear function is just like you add noise, you add the same amount of noise, you add the same amount of noise, or I can add it in certain different functions. So see if I find. Yeah. So this is how it trains, I think. Yeah. This is a good one. So I can either edit like every step I add more noise, regularly more, or I add at the beginning less and then constantly more. So I can use different functions to put on that. And there's like they found out, researchers found out that certain schedulers, like certain ways of adding noise, just work better. So we just accept that and use that noise scheduler. So that's what I'm defining here. Here, just like do a noise, like pull it, I even don't write it. I just get it from the library and then use it, and that's the output. So, and we don't use a linear one. We use a we actually use a linear one. Yeah, that's something that can be changed actually, by the way. So probably it would be better not to use a linear one, but we use a linear one. However, so fine, it works. So go with it. So, and then there's one last thing which is very important for a model, but also we don't need to go into the depth. But if you train a model, you always need a loss function, which kind of tells the model how it's training. There's different loss function. We're just gonna use MSE loss, it's called, but it's just something just accepted. So there's different versions of it. We just go with that one. I would just keep that. So yeah. And we also need an optimizer, same thing. Honestly, this block of code which is coming now, just run it. You know how to prepare the data, you know how to feed the data. And this is part which is just developed in a lot of research over a long time by a lot of people, so we can just take it and use it, basically. So an optimizer, also a model needs an optimizer that helps it how to learn. There's also a different one. We use the Adam one. And then there's a similar to the diffusion. The optimizers have also schedulers, but whatever. That's roughly it. And yeah. And this one this is just to quickly check how long our training will be. So our data loader, because this is basically the whole thing divided by 16, right? So our data loader has so many images because we put it into this batches by 16, so it's just checking. And then we need an evaluate function. This one is just to, while we are training, we will just use that to create images on the fly and also save them. So wait, I forgot. So you will see that once you train it. So this one is just generating a grid of images, like a, like 3x3 grid, image grid, very simple. And this one also not complicated. It's just while we are training, because we want to see how the model develops, like how it gets better, we're gonna create images on the fly. So that's what this is doing. It creates an image and then it makes this grid, like uses this function, makes a 9x9 grid, and then or 4x4 because we have 16 images and saves them. So, but that's just accept it. It's gonna be saved on the name Hugging Face hub. That's also a reason why I wanted that, because it does everything for you. It saves images, it saves information about the training of the model, so it's very handy basically. Yeah. And now next step, this is the training loop, and that's a massive piece of code. You also don't have to write, but we go over it a little bit. So basically, machine learning is always like this kind of machine learning. Yes, it's a lot. It's a lot. So this is just connecting to this Hugging Face. We can ignore that. And this is the training loop. And we just give it a lot of information. I just go to a little bit more important parts. Honestly, really, you don't need to understand that. The only thing you need to is just basically it's going over all the epochs. We told it before how many epochs, right? So it's going over all of them, and then it performs this training operations, and then it looks how well this training is performing. So, and then we save images, we upload them to this hub that we can check it. We save information about how the training is going. All of this going on here. And then there's also, because I also took a lot of code from another GitHub, so there's also things like this, for example, is just libraries to make it train faster and stuff like that. So this is really not, you don't need to get into that. The only thing you may need to change here, so I added, so we push our the checkpoints when it's breaking, or maybe hopefully not breaking, but still our checkpoints every 10 epochs, I said this case. And this is a parameter you can change here. So I saved them to my drive at the moment to just have them double. So this is something you can change. You should change, actually. You should save them somewhere, because it's really annoying if the training breaks and everything is lost. That can happen, and then that's a pain. So yeah, honestly, I think we mainly ignore the training loop. If you are really interested in it, I can explain it extra, but it really goes beyond what we want to do with it, or what you guys need to know for the project and stuff. So I think just take it for that. So yeah, I can explain diffusers more in depth if you want, but I think it doesn't make sense. It's just good that you have the outlines. How the more important is how to feed the data, because this is something we are architects, right? This is really in-depth computer science field, so we don't need to know that like that. Okay. And the last part, which is then running it, which is a ridiculously small part of code. So this is, we just double check to install something. We should have done this at the beginning probably. And then we do, this is training. Only this is training. So accelerate and notebook launcher. This is this library which makes train quicker. And args, arguments, this is all the stuff we need to feed in our training function. So if you see our training loop, it takes arguments. This is our model. It wants the config file. This is what we did before with how many epochs, all of that. It wants our noise scheduler optimizer. We did all that. It wants the data we want to use. It wants our learning rate schedule. As said, ignore it. But then all of that, we defined it up. We need to feed it in here, and then we just run it. And that's actually it. So part we can influence is mainly the config file and the data set. This we better don't touch. Okay. So yeah.
So after we train it, how do we reference or use these data in
Very, yeah, a very
Okay.
good question. That's a little bit so first do the training. That's not as easy as you may think at the moment. What I do now, because I cannot, the training takes quite a while, right? So maybe I just show you something I trained. Let me just look for it on my other screen. Yeah. Oh, and I forgot one thing. What is very important also, because otherwise the training won't work. We need to, so in the config file, at the very beginning, this is really crucial. Here we created, so if we use the push to hub and we created this, we put this output here, the name here, we need to go on Hugging Face. So you need to go on Hugging Face and create a model with the same name. New model. This is the name you chose. And then you put the same thing. So you need to put this name, just copy it, put it here, and then public, I go private, but however you want. And then you have this thing in here and you find it on here. If you click in your profile, this is the models. So this would be the new one, right? And there's nothing in there, but the ones, like, for example, I show you one I trained in the past. And so first I show you the output rate. So here's the samples. This is how this looks. So this is epoch 0, so the model knows nothing. Still, it does already. That's what I said at the beginning. The training is very quick, and then it drops. It's like it's a curve like. Oh yeah, I shouldn't show you. I don't need to tell you. So yeah, that's the first epoch, and then I trained it, I think 100. Yeah, and that's the last one. So this is generated images. This is fully synthetic data, and if you look closely, it fails at some points because it's not perfect. For example, some have definitely too many doors. There's rooms which don't have doors, like this one, for example. So there is a little bit fail of it because the model is not specifically designed to, it's designed to generate any kind of images, not for floor plans. There is also people doing that, but it's a whole different card. But it works okay, I'd say. It works good enough for us. So yeah, that's what you can, if you train, should have as an output. And training metrics. So this is how the training looks. So this is the time. Train 7 hours, by the way, as you can see here, how many steps. And this shows at the beginning, it improves quite a lot, quite steep, and then becomes more and more and more and more flat. So the first hour is already, if you check, like if you just train it shortly, you can see already if it's going into the right direction. And because if it's in the beginning going straight and not down, there's already something wrong. Although because I give you such a rigid architecture, it probably always gonna be okay. So it's more like if you change stuff on your models, then this is important. But for us, but it's good to see that at least once, I think, so to yeah, see you can kind of check some things about, or this makes it more clear. So this is the actual one, but if you smooth it, that's more like the tendency of it, right? So the beginning, it falls very, very quick, and then later, the performance, yeah, drags.
So the batches that we train, or the epochs, it's not always the last one. So basically, it's not always the 100th epoch has the best result, right? Or will it always be the last one has the best result?
So normally there is overtraining, which means this can go up again, and there's another way of overtraining, which means that it trains so hard that it will recreate the data set. So it won't create new stuff, but it will just do stuff the data set already has. But this is a little bit a problem to realize that there is like algorithms for checking that, but I'm not going to teach you that just to. But so it's like roughly if you this probably if you train it longer, this would still go down, but it gets exponentially slower. So it's at some point not really worth it anymore. And the problems it has, right? So there is these small problems I said with the doors, for example, right? This won't fix it, you know. So the longer training wouldn't like really be worth it, because this is the problem with the doors, for example, is something which is more into the general how the data is read, because it's not able to understand that one room should probably only has one door. Although also to be honest, I don't know the data set that good. I think also the data set is not that great. I have to admit that, like, there's eventually better ones. If you look at the images, some of them have also really weird floor plans. So yeah, that's of course also a big point. How is the data set? And yeah.
So if we don't change any number and then just let's it run 100 times and then let's it run again 100 times, then we always end up on the same results, or will the
So
results
that's
be
the
different?
seed. Well, so
We'll have to change the seed in order to change them.
no, but the thing is, you can this is not the only thing it generates, right? Like now I have it on hand. So yeah, let me show you that. So this is the data set you just have open on the hub, the 3, I call it DDPM floor plan 3 128, whatever. So I can now download it from the hub and use it. So I can generate infinitely new images. So I don't need to train it every time. I train it once. It's like baby stable diffusion. Like imagine it like this. So now I can create as many of that as I want. And so you only need to retrain it if either your training fails, you have a different data set, or you want to try a different architecture, like a different kind of neural network where you think it's gonna be better. So, and by the way, also not part of that class, but in general, it's more like there's a lot of stuff out there. So if you're interested you can also just pull stuff from GitHub, try out things. Sometimes you don't even need to write code. That's the sad thing I tell you in the end. But of course, sometimes there is just stuff where people just like have it to a degree prepared for you that you just put data in a folder and it generates for that. For example, stable diffusion can be fine-tuned. So you can train on the already trained model on top of it, and you don't even need code for it. So that's also something you can do. But we want you to generate spatial data like floor plans 3D with it, so not images, right? So yeah, and I just will quickly show you how to, but that's all gonna be, by the way, in the thing I sent you them. And if the training is finished, but it's also, as said, all in the file I sent you, you definitely need to save it like this. This will save it to the hub also. And now I quickly show you how to use one of those. So, so here I connect to that. That's the name of it. And this hopefully works. Yes. Now it's downloading the model. And with this piece of code, I can run it. No, same code. This is the piece of code with torch. No grab means that I don't train it. It's the same function as if I would train it. I definitely make sure it's on CUDA, so on the GPU, and then I generate it and take one of the images. And this, by the way, is my condition. So at the moment it's 9. It's going to do a rather big one. Let's do 5. I'm going to do a middle-sized one. So let's run it. This is rather slow. So if you want to use it, what you asked earlier, if you want to use it in Grasshopper or if you want to use it in whatever, in theory, if you can use Python in the software, you can you train the model here, you put the model in a folder of that software, and then you can reference it from there. It sounds very easy when I say it like this. There's a lot of problems because you need to have a lot of libraries installed. But in theory, that's possible. So you could, in theory, directly call it from these softwares but you don't train it there. You will never train it in one of these softwares. It's also in theory possible, but inherent, like, no, you shouldn't. You should really separate the data creation or the data where you get it from. Then you train the model and then you apply it eventually in one of these softwares. So you could, in theory, generate data with Grasshopper, train it in either Colab or on your local machine or whatever, and then you can use it in Unreal, whatever, wherever you want. Okay, so now, oh, it didn't work. I don't know. What? Yeah. Okay. So this is one I just generated. So you can endlessly generate new ones. That's the least of the problems. As soon as you have a trained model and you reference it correctly, but first try to get to the trained model, I think. Okay. I think did I copy paste that we go over it, or is it fine if I just share the notebook in the end now? How do you feel about that?
Specific question.
Yeah.
So when it generates the floor plans, you can reference, or you can select the ones by the size. But let's say if I want specifically, in this case, if I'm a user that I want a floor plan that has 3 bedrooms, 2 bathrooms, one living room, one kitchen, how would I be able to reference that specific data from the data set or from the model set?
Yeah, well, that was the assignment basically last time. You need to extract that from the data set first.
Yeah.
But that's because the data set, you remember, is like a Excel. Basically, it's like an Excel file, right? Like it's a big table, and there is each of them of these columns of this Excel file. So there's one of them is named bedrooms or something, I think. And then you can count how many bedrooms does it has, and then you can create a JSON file, or you can save it in a text file. But not what I did in this, what I did here, right? I extracted it from the image, right? With the other stuff, you can, but it's not advisable. Like if it's the black background, like how many pixels are black here, I can get easily from the image.
Yeah.
But from if it's more sorry, I need to of course come here. So for example, if I want, like this is probably 2 rooms. I don't know how the data set handles this probably. So if I want to know how many rooms there are, the image is not a really good thing, but our data set, the ones we created the images from, is geometric data. So it saves, this is probably a rectangle, this is a like this is like a polygon, this is a polygon. And you can find this in this data set. So if you want to extract that, I can also help with that, but this is the data is there. It's not like, it's because we don't have images as a base. Our base is like a list of different geometries. So, and they are in a fashion that they say, for example, I don't know, I think this is probably bedrooms, this is living room, this is bath or something. So it will be a table somehow like that, right? And each of the lines is basically a different floor plan. So floor plan 1, floor plan 2. And then here, this would be, if this is bedrooms, and this is the bedrooms, whatever, these 2 rooms, if that would be the B, there would be 2 data items here. So there would be 2 polygons, polygon 1, polygon 2. So you can count how many polygons are there. So then you can extract like a JSON file which says bedroom or living room or whatever it is, 2, bathroom 1. That's something you can extract from the data set. And if you name it the same, then you can put it out from the data set together with the images and then reference it back to the data loader. So this time what we did, we just look at the pixels, but this kind of information we cannot get from the pixels, but we can get it from the data set I gave to you before we create the images even. So yeah.
Yeah, what I was asking is basically after you create these ones, or the new
After again, you mean?
yeah, after the general ones. Can you still reference it? Or it's
The colors are different room types.
but then they won't, in this case, then they won't be able to specify, let's say, how many different rooms are there, so that, because what we were thinking is maybe something is.
But you can specify it on the generation. If you train the model and condition it on that,
yeah,
you can probably tell it how many bedrooms you want, and then it will create a floor plan with that. That although this might not work perfectly, there might be mistakes, but the tendency will probably work. But the output will always be only an image. We cannot change that. If we want another output, we would have to train a completely different model. So that's we are sticking with the images. But since it's so clear colors, you can quite easily still find which pixel is living room, which pixel is whatever you want. And if you think modular, as said, like if you're thinking, oh god, that was very not very straight. So if this is if you work in grids, right? You don't need 128 by 128 dimensions. It would be very smart that one grid is only one pixel, because it's about transporting information. It's not about an image. The image is just a way of transporting information. So if you anyways work with a grid, probably make sure one pixel is one square grid. And smaller image networks are quicker and easier to train, by the way, also.
What happens if we, if every word break out of the grid? How can we still reference this? Can this grid be in different sizes, or
How do you mean half the grid?
like
if it's not square, but it's
that? But yeah, I can see how this thing can be cut into grids that have uniform sizes in there, but
so you want to, but then
Yeah.
you're just back at an image. It's just the thing is more which kind of information do you want to generate? So you could either generate, for example, the colors, which are in this case meaning different room types, right? Or you could generate the height we had earlier, like how high is the building. You could, so what do you want to encode? The thing is, you cannot encode a lot of different things, but several. So, but you also, I mean, there's a lot of different directions. You can either stay with that data set and try to do different things with it, or you can generate your own data set, or you can try to encode really different information into the tensors. But the last one is the most interesting, but for sure also the most difficult. And it's very important that you train, at least with this data set. So the code I'm gonna send you, I think at least one of each teams should train that. I think one team is not present anymore, right? But I think I'm not even best would of course be if everyone trains one, but I think it's fine if one from your one team does it and hopefully has a successful training. And also so we can check on that again. So if you have trouble with the training, ask me we're gonna probably do another where don't bring new stuff, but we just check and see problems you have, how that is going and all.
Yep.
Okay. Do you want me to copy all the rest of it? But probably it's better if I give you to clean with the work one work with the clean one anyway. So.
Yeah.
And can you show me the project especially the team with the grid. Can you show me what you work?
Training.
Yes, so doesn't.
There's something we're doing the important things because this is our module and actually it has different side of a connection which is can combine all the these modules into to create a wall, to create a closure space and so we have a grid like this. It's pretty large, like one grid is 3 meters times 3 meters. And then we can, like, here is our diffusion models and we apply this model to this diffusion models by creating these walls. But not the rooms anymore. It's not it's just doing the spatial division on this side, but not really giving it a function, and we don't have a floor. It's very this one. But right now we are about to change it, and also there's a technical. And right now it's only very they hope like we can explore like the space together, but stack into like a dense larger. Yeah. And about to change the models shape. Yes, yeah, that's the thing, and we're about to change the size of the models and able to nest them together, like
But actually, one thing just what you want to do is maybe difficult because the walls, if you go up to, can you go up to to extract, for example, like this module is in this room, is pretty straightforward. But to extract that here's a wall and here's a door, it's more difficult. Do you know what I mean? But you have like, this is like open, right? So this is maybe this fully closed. But here is open.
Right.
Because here's a door.
Yeah.
So getting the information from the image where there is a door and where not is probably quite difficult. Because if you would like the outline of the room, right? If this is you could see this is like 6 pixels, right? So you could very easily generate that, but that the opening is there, it's more difficult to extract that from here and bring it into something like Rhino, because how do you know it? For example, if you just even take this image and you put like a grid like this on top, and then you can just say for every point, is it in a color, like is it outside? But the door is way more complicated. Let me put it that way. You could try to, because you need to make the pixels into lines or something like that, right? So that's difficult.
So when in the version you're supposed to be not like looking like actually looking the doors like by the connectivity graph. Like if two spaces connect together, they must have a door, like they must have a connection in the sun.
But you don't know where the door is then, right? And that's What you could do, for example, is more, you don't have to stick to that. I'm more like saying, I'm actually more on the side, like you better to be creative with it. So maybe ignore the doors, just generate the outlines of the rooms.
Okay.
And the doors, if you know there's a connection from the connection graph, then just make a random door. You know, it's because you are quite far away, like, you know, it's easy to find that this wall is connecting to this one, right? That's easy to know. But it's quite difficult to know that all of this is here, all of this is even an opening, right? So this and this would be a snipping tool. Yeah, so this is the opening, right? So here even this would be all open, right? I guess. So that's what I'm saying. Like, it's quite, how do you bring that information from here to here? That's even before you can, like, if you even take just an image from the data set without even generating it, that's already trouble, right? Like, how do you get it from an image, the information? Because you have to know the output as an image. As I said, it's not like our data set. So that would be quite easy, but it's quite difficult to find that. It's probably possible, but I think you would waste a lot of time trying to do that. So maybe like finding the outline, or finding the position of the rooms. So, you know, like the outlines is probably a more straightforward direction, I think.
Yeah.
And connectivity, you can have the connectivity eventually, but it's probably difficult to find the actual position of the roof additionally, because there's an extra step even. So I would advise you to probably not do that. So probably you would come up with, this is one color, this is another color, this is, you know, like just different colors, and then you find the positions even.
So, I mean, like in the data, when we are inputting the data, should we like delete the door, or we have to keep the door, but when we translate to our module, we just import it?
So probably, I'm not, but could be because you have such a straightforward quad model, like module. It could be actually, it could make sense that you take each of the floor plans. I'm not sure, I hope. So if you would really take each of the floor plans, mesh a grid on top, and then for each of the points, as I just said before, you check each of the points, you can check in which room they are, right? That's something you can do with the data set I gave you even. You would just need to create points at a position around this image kind of, and then check for the color it's on.
Yeah.
Except if it's like, when you can take off the walls, and then you would create a new image or whatever, where just like this module is fully blue, or this module is fully, so then you could even train the model on the module dimensions, you know, instead of saying I have somehow an output and after I try to relate it to my module, it would be good to just take the data set and transform it in a way that it already fits your module. That's
Clear.
that's something you could think of.
Yeah. Thank you for that. Yeah, that's the word first, because we have to like we have to like tuning it successfully first.
Yes, but I think.
But right now it's a good direction to consider.
So basically, you know, like what I'm teaching is like a separate like tech thing, right? So the final assignment is doing all the three. You had the smaller homeworks, right? And ideally, and now the last assignment is kind of like specified more again, but it's train. I want you like train a model with a condition, and either with the one I showed you, but or the ones you expected from the classes before. So maybe would you ask for the number of rooms or connectivity graph? Although the connectivity graph, I'm honestly not completely sure if that even works well, that kind of model. But yeah, so that's mainly the training, because it's really not easy. It's the main assignment for my class. And then for your project, you should probably train first one and try how you get along with it, and then train. Yeah, you can try to adapt your data. And also, I forgot one thing. Probably it's good for the training to buy Google Colab Pro, because it's otherwise really slow and probably also breaks, because the normal Colab also always breaks after like I think 2 hours. I mean, if you don't move the mouse, stuff like that. So in Google Colab Pro, it's like I think it's £10 a month. So if you share it as a team, I think that for the 100 epochs you probably need. So, yeah.
This is what we ended up with in the end of last time, where we were trying to design this data three-dimensional component that embeds certain architectural characteristics. So sometimes it's columns, might be a corner, might be a wall, and then what we're thinking is that using AI will come to, or the computational method, that first you basically define a plot, separate it into grids, and then within these grids that you set up the points where, let's say, it's the beginning points for where commercial or residential different area starts to grow, and then in those places you start to have the users to start taking control, taking more participation in this case. They start creating their individual spaces, and that's why I was asking you. So maybe someone wants an individual studio, so it's just going to be a bedroom with a toilet, with a kitchen. Someone wants an entire family or something else. And yeah, and then ideally what we were thinking is that you would have different variations of the same kind of residential or the same kind of spaces, and then they will all be grouped up, be put into the set located by the computational power that defines a certain part or defines the site. And that's in the last one what we aim to have, but this is all done manually. But right now what we're trying to do is to refine those three-dimensional kind of components to make them more, to give them more kind of idea with the sense to connect with a bounding box that is similar, so that they can all internally connect. But all of this can be done manually, but how to achieve the specific thing that we want, let's say, how to use these elements to fit to a certain floor plan that's not just AI generated, but hence, let's say, the preferences of the users.
Actually, because you think so modular and this connectivity, actually, your case is very much what Cesar and Federico did last year, is like a wave function collapse algorithm. It screams that, actually. Do you know that algorithm? Can you Google the wave function collapse algorithm? The problem is, yeah, I think they don't teach it here, but
Oh, I think I do. Isn't that something like a, wait, is WASP based on this?
not really, because wave function collapse must be
No.
voxels or pixels. It must be the same size. And WASP is based on collisions. So WASP is more like adding things and see if they collide and come up. But this one is really filling like a whole grid. But yeah, it's a very popular algorithm in the school. I don't know, but yeah, it's not difficult compared to AI, but it's also not easy.
Okay.
So
Is this another entire kind of setup?
well, last year the tech tutoring was for that.
Alright. I mean, this is what we are trying. What we're thinking. This in this case is still experimental. So we're not sure if they really want something like this or not. But that's what we're kind of thinking of to target it to set of these, but
Just the similarity of that, you know.
yeah. Now I see exactly.
So I think if you wanna go in that direction, but yeah, talk with them first. I'm not the main tutor. I can really like don't listen to them. But it's basically the
I thought they
But yeah, I don't know. I mean, they're kind of they didn't want us to know exactly have an exact points about what we are aiming for, but at the beginning of this term, so basically
but you know a little bit Python, right?
just a little.
But a little more than who's the best Python coder from you guys? Do you know?
Probably today.
So, but is he in your team? No.
No, he's in group one.
Yeah, because I found that there's a very easy Python implementation of this,
No,
but in 2D, but 3D is not difficult to make then, but
I mean, if it is 2D, then we'll be. I mean, we're
I
basically.
think if you go in that direction, it has to be 3D, that's because they did, yeah. If it's AI, you maybe can jump the shark without, because it's different, but with that.
Yeah, and that was the thing. Like, if it was just a 2D floor plan, then I wouldn't be able to know because a lot of these different elements embed 3D-dimensional characteristics, so I can't just based on a simple 2D diagrams. And that was the reason why I was asking if there's anything of them.
I mean, you can, but the data is.
Yeah. But yeah, this is what we are thinking of progressing towards, and to develop, and that would also help in a sense to help us develop a clearer rule or hierarchy in how to generate or how to create these kind of large architectures, because currently it's done manually, it's imaginary, it's visionary, it's not really using the AI to set this up.
I think, though, for example, using an AI to generate the general, like the urban thing is probably quite far-fetched.
Yeah.
So it would be probably, you can like maybe make that more traditionally computational, quote unquote. And then AI could be more come into play if you was use that like certain, if you have singular modules, and then you maybe can generate plans for them with AI. But the whole urban plan has way more variables.
Yeah.
It's even way more complex. So I think that's a very high aim. So I'm
Yeah, that's yeah. We're like so stuck on the computational part because all of this, if we just talk about it, it sounds like it's gonna work, but in the actual practicality, it's
yeah, but I think also you cannot it won't be possible to combine all of the methods, so
yeah.
maybe one method is conceptual and one you actually implement, it's not.
Definitely, yeah. And I think that's also why Cesar and Federico are saying to all of us to simplify your system. Do not try to solve all the problems, but choose one. So I guess in that case, we'll talk to them about how our thing can work then. And so next class will be our last tutorial with you.
So basically now I sent you that in clean, and then you train, and then we just have a lesson where we check how the training went and for the last final. But I don't teach any extra. That's the thing, because you should know basic Python, how to use the data set, how to load the data set, how to train an AI.
Yes.
So that's, of course, but the thing is AI said a lot of different ones, right? Of course, I can only show you one.
Yeah. Okay, thank you.
Thank you.
Thank you.